Welcome to this video, introducing you to track geometry. First, let's get an understanding of what is meant by track geometry. Track geometry is the design and maintenance of the longitudinal and vertical alignments of the railway track, along with the relation of the rails to each other, through gauge and the application of Cant. In this video, we will look at the basics of track geometry. This will include the difference between vertical and horizontal geometry, and look at the key parts of each, and then how track geometry is maintained. Before we get into more detail, why is good track geometry so important? Good track geometry design is important for a number of reasons. It ensures good interaction between wheel and rail. This minimizes wear on the rails and the wheel along with other components. It is maintainable after installation, to ensure the ongoing safe passage of trains. It provides a comfortable ride for passengers and stability for freight loads. When looking at the geometry of the track, we split it into horizontal and vertical planes. The horizontal alignment is the left and right turns of the track. Think of the corners on the road. The vertical alignment is the rising and falling gradient of the track, as it climbs up and descends slopes, along with the curves linking these gradients. Think of going up and down hills in your car. Let's have a closer look at horizontal alignment. As we have already said, the horizontal alignment is the left and right-hand turns the railway takes. Ideally, we would want a railway to be straight, taking the shortest route. This allows for faster train speeds and also reduces the forces on the track components. In reality, natural features such as hills, rivers and valleys influence where we can put a railway. As well as that, there are buildings and roads that have already been built to worry about, as well as where the stations the railway is looking to link together are. If we are renewing existing track, it will already have a corridor that it is in, that cannot be easily changed. All this means that we need the track to be able to go around these obstacles. This is where horizontal geometry comes in. Horizontal geometry in its most basic form is a combination of straights, curves, and transitions between the two. A curve is handed to describe its direction of travel. For example, a curve that goes around to the left will be a left-handed curve. It may also be described as its flexure, but this term is normally used when describing junction layouts. Straight track, as the name suggests, is straight between 2 points. It will normally have zero cant applied to it. Cant is the relative difference in height between the two rails. We have done a video on cant, so for a more detailed explanation please hit the link in the description or on screen. Transitions link straight track to curves. They are curves with a radius varying through their length, that slowly tightens until it reaches the radius of the curve it is linking to. Similarly, the cant is increased, or built up through the transition until it reaches the value designed for the curve. The rate at which the cant increases is called the rate of change of cant. The use of transitions reduces the sudden change of forces acting on the trains. Curves in track have a constant radius. The radius can be as low as 200 meters for passenger trains, or 150 meters for freight routes. In exceptional circumstances, it can be as low as 125 meters. Curves will normally have a constant cant applied to them. In addition to simple, single, curve arrangements, there are also compound and reverse curves. Compound curves are where curves of similar flexure are placed one after the other. This could be because the curve needs to become tighter or looser in radius. In between these two curves, there should be a transition, the same as between a straight and a curve. A reverse curve is when the two curves are of different flexure or hand. In this case, two transitions are required. The transitions are placed either side of the reverse point. At this point there will be zero cant, and it is here that the change of curve direction occurs. There are specific requirements around the design of transitions, which will be covered in another video, linked in the description. In some cases, a transition cannot be fitted in, so a virtual transition is used. A virtual transition is an instantaneous change in geometry, without a physical transition length. Again, these will be covered in another video, linked in the description. As well as turning left and right, we also need to think about going up and down. This is known as the vertical profile, or vertical alignment. The world cannot be made completely flat for the railway, so trains do have to go up and down inclines. However, given their weight, especially freight trains, they are only capable of getting up inclines of a certain gradient. More traction effort is required, and this also puts further stresses on the rails, which leads to defects. Another reason vertical alignment design is important is for ride quality for passengers. We don't want them to feel like they are on a roller coaster. Similar to horizontal geometry, vertical design consists of a series of constant gradients and straights. These are joined together by vertical curves. In vertical design we do not have transitions. The gradients of the straights are expressed as 1 in, or as a percentage. The 1 in refers to how far you have to travel to rise or fall 1 meter. The percentage change is another way of expressing this. The vertical curves between the constant gradients are designed to reduce the changes in gravitational force acting on the train when moving from one gradient to another. They should be 25 meters or more in length. Once the track has been designed and installed, that is not the end of the story. It then needs to be monitored and inspected as it's used by trains. It is inspected throughout its life to check for deterioration and to trigger maintenance to ensure it is safe for trains to use. In the UK, a special fleet of trains, known as track recording vehicles, are used to inspect the geometry of the majority of the track. They run all over the network, covering track at set frequencies depending on its usage, measuring track quality data. A key advantage of using train-borne recording is that the measurement shows how the track acts while under the load of a train, known as dynamic inspection, highlighting issues that may not be visible under static inspection. Some areas, particularly crossovers and terminal platforms, where it is not practical for the recording trains to be routed to record, have to be manually measured. The train measures and records different parameters as it travels along the track. The parameters measured are top. This is measured on each rail, and highlights dips, or high points on each rail. These could be caused by dip joints or welds that haven't been ground off properly. Alignment. This monitors the track for sudden lateral changes in the track path. Gauge. By using lasers to measure the distance between the rails, the train highlights areas of wide or tight track gauge. Wide gauge is more common and can be caused by base plate shuffle or failure of the housings in the sleeper, allowing the rails to be pushed apart under the load of passing trains. Twist. Twist faults are when there is a sudden change in cross level between the two rails, measured over a 3-meter distance. They can be caused by voiding below one end of the sleeper and pose a significant risk of derailment if allowed to deteriorate, especially to short-length freight wagons. Cyclic top. Cyclic top is a series of dips in a route, looking like a wave. They are a problem for trains, particularly freight with its stiff suspension. They cause a cycle the loading and unloading of the suspension. This buildup of energy can cause trains to eventually jump off the rail head. After the train has recorded all these geometry faults, they are categorized by severity and given a time frame in which they must be fixed. They are then sent to the maintenance teams for them to plan rectification. There we have an introduction to track geometry. To sum up, track geometry design is important for the performance of the railway. It is split into horizontal and vertical planes, each with its own properties and design considerations. It requires ongoing inspection, monitoring, and maintenance. For more information on horizontal and vertical geometry design, and the maths behind it, visit our channel and subscribe so you don't miss our new videos.